Cartesian coordinates to one represented by components in cylindrical coordinates. After we work through this example, we will come up with a general expression for doing this vector conversion. But to work through this example, we're going to do it by drawing figures and developing a mental representation as we do this conversion. The problems I will ask you on homework assignments or on exams can be done in this way by drawing figures and figuring out these conversions. This way you'll show that you have a conceptual understanding of the different coordinate systems and converting between them, and it'll be more likely that you'll get the answers correct. In this example, I'm assuming we have a uniform electric field intensity everywhere. So at our 4 points, the electric field intensity is 10 volts per meter in the x direction. Let's start with this first point here at 1, 0, 0. So here's the point at 1, 0, 0 in Cartesian representation. The cross-section in the xy plane of the cylinder that goes through that point will be a circle of radius 1 meter. So that will be the rho component. So here is our plane that goes through that point that's attached to the z-axis, that semi-infinite plane, and we see that the angle it makes with the x-axis is 0. So our second component, the value of phi, is 0. And in Cartesian coordinates and cylindrical coordinates, the z component is the same. So here is our representation of this point in cylindrical coordinates. In a previous video, we came up with these equations for converting a point from a description in Cartesian coordinates to cylindrical coordinates. So you could look up these equations and plug in these values and compute your cylindrical coordinates, but you can see in this simple problem, just drawing a picture, you can essentially just write down the cylindrical coordinates. So here's our first entry. Now let's look at representing the electric field intensity by components in cylindrical coordinates. A common error I will see on an exam is using this set of equations to do vector transformations. The conversion of points and vectors between descriptions in different coordinate systems are two completely different things. Here we have our electric field intensity at this point. It has magnitude of 10 volts per meter and it's in the x direction. At this point, this is our unit vector in the x direction. This is our unit vector in the y direction. Also at this point, this is the unit vector in the rho direction, the direction of increasing rho component, this cylinder getting larger in radius, and this is the direction of the unit vector in the phi direction. So at this point, the unit vectors in the x and the rho direction are the same. So at this point, the electric field intensity is 10 volts per meter in the rho direction. So finding the vector representation in cylindrical coordinates is completely different than finding the representation of the point in cylindrical coordinates. Let's look at our next point. The cylinder that's centered on the z-axis that goes through that point, here's the cross-section of it, and it has radius 1 meter. So that's the rho component. The plane that goes through that point that's attached to the z-axis is this plane right here. The angle that plane makes with the x-axis is pi over 2 radians. So that's the phi component. And finally, the z components are the same in the cylindrical and Cartesian coordinates. So there is the point in cylindrical coordinates. So here's that point, and now we're going to find the representation of the vector using components in cylindrical coordinates. So at this point, here is a representation of our electric field intensity of 10 volts per meter in the x direction. Here are the unit vectors in the x and y directions. So this unit vector points in the direction of increasing x value, this unit vector in the direction of increasing y value. At this point, the direction of increasing rho is the same as the direction of increasing y, so here is our unit vector in the rho direction. For this angle getting larger, that's pointing to the left here, so this is the unit vector pointing in the phi direction, in the direction of increasing phi component. So at this point, a sub phi is equal to minus a sub x. So a sub x is equal to minus a sub phi. So the electric field intensity at this point will be 10 volts per meter in the minus phi direction. So here's that entry. So let's move on to our third point. So here's the point at Cartesian coordinates -1, 0, 0. So the cylinder centered on the z-axis that goes through that point will have a radius of 1 meter, so that's the rho component. The plane attached to the z-axis that goes through that point is this one right here. So the angle it makes with the x-axis, which is our phi value, is pi radians. And the z components are the same. Here is this point in cylindrical coordinates. Now let's find the representation of the electric field intensity with its components in cylindrical coordinates. So at this point, here is our electric field intensity of magnitude 10 volts per meter in the x direction. Here are our unit vectors in the x and the y directions. And here is our unit vector in the rho direction, in the direction of increasing rho component. And here is the unit vector in the phi direction, in the direction of increasing phi values. So a sub rho is equal to minus a sub x, and our electric field intensity at this point here becomes 10 volts per meter in the minus rho direction. Okay, so now we move on to our last point, and this one's going to be a little bit different. And it's going to lead into our discussion of the general way of representing this conversion between vector representation in the Cartesian and cylindrical coordinate system. Here is our point, root 2 meters minus root 2 meters, 0. The cross section of the cylinder that goes through that point that is centered on the z-axis is shown here. So the radius of that cylinder is right here. So this radius is rho. We have a right triangle here. Each side is the square root of 2 meters. So rho is the square root of the squares of the two sides of this right triangle. So rho is equal to 2 meters. This is the plane that's attached to the z-axis and goes through our point. So our phi component, the angle that plane makes with the x-axis, is this one, and it is 7 pi over 4 radians. And the z components are the same. Here are the cylindrical coordinates for this point in Cartesian coordinates. Let's now find the representation of our electric field intensity in terms of its components in the cylindrical coordinate system. So at this point, here's our electric field intensity of 10 volts per meter in the x direction. Here are our unit vectors. This one is the unit vector in the rho direction, pointing to increasing values of rho, and this one is the unit vector in the phi direction, pointing to increasing values of phi. Our electric field intensity at this point is going to have a component in the rho direction and a component in the phi direction. So we have to find the rho and the phi components. Since phi is 7 pi over 4 radians, this angle here is pi over 4 radians, which means this angle and this angle will be pi over 4 radians. Looking at this right triangle, this side, which will be the rho component, will be the hypotenuse 10 volts per meter times the cosine of pi over 4. Similarly, this side, which is the phi component, will be the hypotenuse 10 volts per meter times the cosine of pi over 4. And the cosine of pi over 4 radians is root 2 over 2. So the electric field intensity is 5 root 2 in the rho direction plus 5 root 2 in the phi direction volts per meter, and it's also equal to 10 volts per meter in the x direction. You should now have a clear mental representation that converting the description of a point in space from Cartesian coordinates to cylindrical coordinates is completely different than converting the representation of a vector at that point from its components in the Cartesian coordinate system to its components in the cylindrical coordinate system. In this example, I picked points and vectors where if you drew a figure, it was easy to make these conversions. Let's look at how, if you were given just some general vector, how you would make this conversion. Here we have some vector at a point in space represented with its components in the Cartesian coordinate system. We could equally represent this vector with its components at that point in the cylindrical coordinate system. Let's take the dot product of our vector with the unit vector in the rho direction. Taking the dot product of this representation of our vector with a sub rho will give us just the component of the vector in the rho direction. Taking the dot product of this representation of our vector with a sub rho will give us e sub x, ax dot a rho, plus e sub y, ay dot a rho, and a sub z dot a sub rho is 0. Given a vector at a point described by its components in the Cartesian coordinate system, to find the e sub rho component in the cylindrical coordinate system comes down to just finding these two dot products between these unit vectors. Let this be the point where we have this particular vector representing our electric field intensity. So the coordinates of this point are rho, phi, and z. Here are the Cartesian and cylindrical unit vectors at this point. This angle is the same as this angle, so it is phi. Since the angle between these two unit vectors is pi over 2 radians, this angle is pi over 2 minus phi. And similarly, since these two unit vectors are at pi over 2 radians, this angle here is phi. To find the dot product between a sub x and a sub rho, we look at this figure. The magnitudes of the two unit vector are 1, and the angle between them is phi, so we have a cosine of phi. So ax dot a rho is equal to the cosine of phi. To find ay dot a rho, we look at this figure, and we get ay dot a rho is equal to cosine of pi over 2 minus phi, which is the same as sine of phi. So to find the e sub rho component, it's ex cosine of phi plus ey sine of phi. To find the component in the phi direction, we take our electric field intensity vector and dot it with a sub phi. Dotting this form of our electric field intensity with a sub phi will just leave us with the phi component, because a rho dot a phi is 0, az dot a phi is 0, and a phi dot a phi is 1. Dotting this form of the electric field intensity with a sub phi will give us e sub x, ax dot a phi, e sub y, ay dot a phi, and az dot a phi is 0. So we have to find these two unit vector dot products to get e sub phi. So again, here is some arbitrary point and the corresponding unit vectors in the Cartesian and the cylindrical coordinate systems. The point is at rho phi, so this angle is phi, this angle is pi over 2 minus phi, because the unit vectors in the x and the y directions are at right angles, and since the unit vectors in the phi and the rho directions are at right angles, this angle is phi. The angle between ax and a phi is pi over 2 plus phi, so ax dot a phi will equal the cosine of pi over 2 plus phi, and the cosine of pi over 2 plus phi is the same as minus sine of phi. So this dot product will be minus sine of phi. The dot product of ay with a phi will be cosine of phi, so this dot product is cosine of phi, leaving us with e sub phi is equal to minus e sub x sine of phi plus e sub y times cosine of phi. Let's collect our results then. Here is our previous result for the component in the rho direction, and the components in the z direction are the same between the Cartesian and the cylindrical coordinate system. So here are the general expressions for converting a vector from representation in Cartesian coordinates to one in cylindrical coordinates. For the problems I will give you, it will be much simpler and quicker to just draw figures and calculate the conversions than going and applying these equations. And it will also reinforce your understanding of these conversions between Cartesian and cylindrical coordinates.